Today we are discussing about charge conjugation operator, or in other words we can say it is a particle-antiparticle operator. The concept of charge conjugation is an important symmetry operator which is used to establish a relation between the negative energy solution and anti-parallel state with positive energy. The Dirac equation in the new form in terms of a charge conjugate function psi c is written by changing minus e to plus e, that is electron to positron, or we can say the charge conjugation operator c operating on a wave function gives its antiparticle. The Dirac equation gamma mu del over del x mu plus mc upon h cross psi x equals to 0 in presence of an electromagnetic field. We can substitute P mu equals to P mu minus E A mu upon C, where P mu is the fourth momentum and small p is the linear momentum, and it is described as minus iota h cross del over del x. Or we can say minus iota h cross del over del x mu equals to minus iota h cross del over del x mu minus E A mu upon C, where A mu is the vector, fourth vector, and defined as A iota phi upon C. So that we can say del over del x mu is corresponding to del over del x mu minus iota E upon h cross C A mu. As the Dirac equation for particle in presence of an electromagnetic field can be represented as gamma mu del over del x mu minus iota E upon h cross C A mu plus mc upon h cross psi equals to 0. Now for the position we replace E to minus E, so the Dirac equation for antiparticle can be represented as gamma k del over del xk plus iota E upon h cross C ak plus gamma 4 del over del x4 plus iota E upon h cross C a4 plus mc upon h cross psi dash equals to 0. Now consider an operator which is related such as psi dash equals to c psi star. Then this equation number 2 will become as gamma k del over del xk plus iota E upon h cross C ak plus gamma 4 del over del x4 plus iota E upon h cross C a4 plus mc upon h cross and C psi star x. This is equation number 3. Now taking the complex conjugate of this equation and multiply it by C star inverse on LHS, we can get this result. Finally, C star minus 1 gamma k star C star del over del xk minus iota E upon h cross C ak minus C star inverse gamma 4 C star del over del x4 plus iota E upon h cross C a4 plus mc upon h cross psi x equals to 0. This is equation number 4. Now comparing equation 1 and 4, we get C star minus 1 gamma k star C star equals to gamma k and C star inverse gamma 4 star C star equals to minus gamma 4. As we know, gamma 1 and gamma 3 are the imaginary matrices and gamma 2 and gamma 4 are the real matrices. Then equation 5, this equation will be satisfied if we take C equals to iota gamma 2 and C star equals to minus iota gamma 2 star, that is equals to minus iota gamma 2. Since gamma 2 is real, so gamma 2 star equals to gamma 2 and C star inverse equals to iota gamma 2. Now for k equals to 1, the LHS side of this equation iota gamma 2 gamma 1 star minus iota gamma 2, that gives minus gamma 2 gamma 1 gamma 2, and this equals to gamma 1. And for k equals to 2 in this equation and substitute C star inverse equals to iota gamma 2, we get gamma 2, gamma 2, gamma 2, and this is equals to gamma 2. This is the right hand side. Similarly, for k equals to 3 and k equals to 4, we get LHS equals to RHS. This means this equation, the relation is well defined, and this operator is called a conjugation operator. Now the CPT operators for Dirac spinors, that is called the Dirac CPT theorem. If we define three operators together, we can find the correspondence between the original and transformed function as charge conjugation C psi dash equals to psi dash psi C iota gamma 2 psi star x. Space reflection or parity defined as psi dash means p psi x equals to exponential iota phi gamma 4, and the time reversal t is defined as psi dash t psi x equals to iota gamma 1 gamma 3 psi star x. Thus, CPT psi dash x means iota gamma 2 exponential iota phi gamma 4, then iota gamma 1 gamma 3 psi star x, and this gives minus gamma 2 exponential iota phi gamma 4 gamma 1 gamma 3 psi x, or after rearranging that, we find this is equals to exponential iota 5 gamma 5 psi x. As you know, gamma 5 equals to gamma 1 gamma 2 gamma 3 gamma 4. So we can write CPT psi dash equals to exponential iota 5 gamma 5 psi. This is called the CPT theorem. Now the bilinear covariant or Dirac invariance and their transformation behavior under Lorentz transformation. By forming product of gamma matrices, it is possible to construct 16 linearly independent 4x4 matrices, which often appear in the application of Dirac theory. The combination of 4 gamma matrices are gamma 1 square, gamma 2 square, gamma 3 square, gamma 4 square. This is one combination. Other is the gamma 1, gamma 2, gamma 3, gamma 4 individual. These are the 4 combination, and 6 combination are gamma 1, gamma 2, gamma 1, gamma 3, gamma 1, gamma 4, gamma 2, gamma 4, gamma 2, gamma 3, and gamma 3, gamma 4. And next 4 combination are gamma 1, gamma 2, gamma 3, gamma 1, gamma 2, gamma 4, gamma 2, gamma 3, gamma 4, gamma 1, gamma 3, gamma 4, and the one combination is gamma 1, gamma 2, gamma 3, gamma 4. This means 1 plus 4, 5, 6, 11, or 4, 15, and 16. There are net 16 combination of the 4 gamma matrices. Now we can classify 16 component combination as follows. First is the identity, and the number is 1, and it is the scalar. Second is the gamma mu. This is the independent product, gamma 1, gamma 2, gamma 3, gamma 4. The number is 4, and this is the vector form. And gamma mu, gamma nu means this is the tensor or second rank tensor. And fourth is the iota gamma lambda, gamma mu, gamma nu, and this is the pseudo tensor. And gamma 1, gamma 2, gamma 3, gamma 4, this is the pseudo scalar. This means this represents the pseudo scalar. Okay, this is the identity, this is the scalar quantity, this is the vector quantity, and these 6 are the tensor of second rank, and this is the pseudo tensor. Now the physical observation in the Dirac theory are bilinear in terms psi bar x equals to gamma n psi x, where gamma n is one of the 16 linear independent 4x4 matrices that can be constructed out of the 4 Dirac matrices. The combination of psi bar x, gamma n psi x is called a bilinear covariant, and gamma n is called the bilinear density, and psi bar x is known as the adjoint spinors. The following property of gamma n are easily verified. We know that from Lorentz transformation, psi dash equals to s psi x. Its Hermitian conjugate can be written as psi dash x dash dagger equals to psi dagger s dagger. Now multiply this equation by gamma 4 on right hand side. We can write psi dash equals to psi dagger gamma 4 psi dagger gamma 4. or we can say this is equals to psi dagger gamma 4 S inverse, or psi bar dash equals to psi bar S inverse. Now for the parity operator, psi dash can be represented as P psi x or its Hermitian conjugate and multiplied it by gamma 4 on RHS on both sides. We similarly get psi dash equals to psi bar x gamma 4. Now for bilinear density, psi bar x gamma n psi x equals to, if you take gamma equals to identity, then we can write it psi bar x I psi x equals to psi bar dash I psi dash. Under the Lorentz transformation from equation 1 and 2, we can write psi bar x S inverse as psi x, or we can write it as psi bar psi. Now the parity operator, we can write the psi bar I psi x equals to psi bar dash I psi dash, or we can say psi bar x gamma 4 P psi x, or we can write psi bar x psi x, since we know P equals to gamma 4. So we can prove for this one. If we take gamma equals to gamma mu, then psi bar x gamma mu psi x can be written as psi bar x gamma mu psi dash x, and under Lorentz transformation we can write it as psi bar x S inverse gamma mu S gamma S psi x, so that we can write psi bar gamma mu psi x equals to psi bar A mu mu gamma mu psi, or we can write it as A nu nu psi bar gamma nu psi. And the parity operator, we know that P parity operator is equals to gamma 4, so we can write it as psi bar x gamma 4 gamma mu P psi x, or if we take mu equals to k, then we can write it as minus gamma 4 gamma k psi x. And for nu equals to 4, we can write it as psi bar gamma 4 gamma 4 gamma 4 psi x equals to psi bar x gamma 4 psi x. Now the third property is the, if you have sigma mu nu equals to minus gamma mu gamma nu, where nu is not equals to nu, so we can write psi sigma nu nu psi dash equals to minus iota psi dash gamma nu nu psi dash, and under Lorentz transformation this can be written as minus iota psi dash S inverse gamma nu and S psi x, or we can write it as minus iota psi bar S inverse gamma nu S inverse gamma nu S psi x. Or we can write it as minus iota psi bar x A nu alpha gamma alpha A nu beta gamma beta psi x, or we can write it as A nu alpha A nu beta psi bar x sigma alpha beta psi x. And under the parity, we can write as psi dash sigma nu nu psi dash equals to psi bar dash sigma kl psi dash, or we can write as sigma kl is equals to minus iota gamma k gamma l, and after substituting p equals to gamma 4, we get psi bar x sigma kl psi x. If we take l equals to 4, then we can get the psi dash sigma nu psi dash equals to minus iota psi dash gamma k gamma 4 psi dash, or we can write it as minus iota psi bar gamma 4 gamma k psi, or we can write it as psi bar x minus iota gamma 4 gamma k psi x, and minus iota gamma 4 gamma k is the sigma k4. So we can done it using the Lorentz transformation. This is the Dirac invariance or bilinear covariance and their transformation behavior. Thank you.